We're often told these huge global challenges, climate change, energy demands, feeding a growing population that they need separate fixes, right? Each one this massive problem unto itself.
Exactly. Siloed thinking.
But what if the real breakthrough isn't a single isolated solution, but actually a radical active connection? What if the answers lie in combining forces in a truly innovative synthesis?
That's a really powerful idea.
Today on the Deep Dive, we're plunging into a groundbreaking idea we're calling carbon alchemy. Now, this isn't just about combining a few concepts, it's a transdisciplinary synthesis. It melds seemingly disparate fields like synthetic biology, AI, cutting-edge genetics, and even climate engineering.
Fields that usually stay in their own lanes.
Right, into something far greater than the sum of its parts. Think of it as a true invention alchemy. Our mission for you today is to give you a shortcut, basically, helping you understand how these incredibly powerful technologies, which are usually studied in their own silos, can actually combine, work together, and, reshape our world for the better. We'll explore some fascinating prototypes, ranging from the, let's say, eminently practical to the truly visionary. And importantly, we'll really examine the ethical considerations and the real-world feasibility, which are so vital.
Absolutely crucial.
You'll walk away from this deep dive, hopefully, with a fresh perspective on how technology and ecology can not only coexist, but maybe even truly harmonize to create a sustainable future.
And what's truly fascinating here, and really what drives this entire concept, is that while each of these scientific revolutions is incredibly powerful on its own, they also each face a distinct set of challenges, limitations.
Yeah.
And when we step back and, connect this to the bigger picture, it highlights precisely why a synthetic approach bringing these elements together isn't just a good idea. It's actually crucial. It's absolutely crucial for tackling the sheer complexity of our interconnected global crises.
That makes sense. We simply can't solve interconnected problems with siloed solutions.
Exactly. You just can't.
That's a crucial point. So, okay, to really understand this alchemical process, we first need to look at the individual elements in their raw form, right?
Break it down first.
What are these technologies doing on their own, and what are their current limits before we even start thinking about combining them? Let's start with, life itself specifically, how we're learning to engineer it.
Precisely. A great place to start.
First up, synthetic biology, essentially applying engineering principles to living systems. I mean, it sounds like something out of a futuristic lab, right? Designing and constructing organisms with predictable behaviors.
Yeah, science fiction almost.
But it's very real and already yielding some incredible insights.
Oh, indeed. We're seeing groundbreaking work. For instance, you look at researchers like Lee Smith and their team, they're engineering microbes to convert greenhouse gases into valuable products.
How does that work exactly?
Imagine tiny biological factories. They're essentially eating carbon dioxide and turning it into things like bioplastics, biofuels, or even potentially food substitutes. And another really promising area is bioremediation, using these same tiny biological engineers to degrade pervasive pollutants. Think about complex compounds like polycyclic aromatic hydrocarbons or those, notorious PFAS forever chemicals.
Ah, right. The ones that are so hard to get rid of.
Exactly. The potential for cleaning up our environment is just enormous there.
That sounds absolutely incredible. I mean, microbial cleanup crews, carbon factories. But if it's so great, why aren't they everywhere already? What's holding them back?
Yeah, that's where the real-world limits come in, and it's a critical insight. Currently, the biggest barrier isn't always the science itself, it's often the economics.
Ah, money.
Right. Low carbon prices make it really difficult for these biologically derived products to compete commercially with the cheaper, fossil-based alternatives that are already established.
Okay, that makes sense. What else?
On top of that, when you try to deploy engineered organisms out in complex natural environments, they often struggle. They have a hard time outcompeting the native microbial communities that are already there, adapted to that specific niche.
Right, survival of the fittest, essentially.
Pretty much. And of course, there are significant regulatory and safety concerns, understandably so. These limit their widespread field deployment.
Okay, so economic hurdles, biological competition, and regulations. But is there optimism?
There is. Lee Smith's team, for example, they're quite optimistic that integrating synthetic biology with digital technologies, things like nanotechnology, the Internet of Things, and especially artificial intelligence, could be the key. The key to overcoming these deployment hurdles.
How would that work? AI, helping microbes?
Yeah, imagine synthetic biosensors detecting pollutants in real time. Then AI, analyzing that real-time environmental data, could dynamically optimize the behavior of the engineered microbes. It could trigger specific metabolic pathways, maybe, to make them more effective just when they need to be.
Huh. So it's not just about creating the superbug, but also giving it the intelligence and guidance to know what to do, where to do it, and when.
Precisely. Intelligent direction.
And beyond cleaning up, can synthetic biology help us, pull carbon out of the atmosphere directly, actively remove it?
It absolutely can. And this brings us to what we call negative emissions technologies, or NETs.
Nets. Okay.
Researchers like Lojal and Wodak have assessed synthetic biology's role here. They highlight its ability to alter or even create biological pathways that convert greenhouse gases into useful chemicals, things like biomass or even calcium carbonate.
Like making rocks out of CO2.
Sort of, yeah. But they make a really crucial distinction. Simply substituting fossil-based industries with biological production, while it's positive, it's kind of like just taking one's foot off the accelerator.
Right, you're slowing down the problem, not reversing it.
Exactly. It reduces new emissions but doesn't actively remove what's already in the atmosphere. The more ambitious goal, and arguably the necessary one, is direct carbon sequestration, truly removing existing carbon from the cycle.
That's a good distinction, really, removing carbon, not just like making new stuff with it. But are there limits? I mean, can we push these biological systems that hard? It sounds energy intensive.
There are indeed limits. Lodgell and Wordak point out that engineered organisms face what they call hard biological limits, things like metabolic energy trade-offs.
Meaning?
Well, carbon fixation, for example, is an energetically demanding process. Trying to transfer these complex pathways into common industrial hosts, like E. coli, is still very challenging. It's a bit like trying to run a marathon on a diet of only sugar. It's just not optimal. The organism needs sufficient energy to perform these demanding tasks.
Got it.
And then you have what they call soft social limits, which basically encompasses all the ethical and economic concerns surrounding this kind of technology.
Right. But progress is being made.
Oh, yes. There's been a truly exciting recent breakthrough from Seaborg and colleagues. They've developed something called biointegrated carbon capture and utilization, or BICCU.
BICCU. Okay, what's special about that?
This innovative approach uses a type of microbe called methanogenic archaea. These microbes convert captured CO2 directly into methane, using green hydrogen as the energy source.
Methane. Isn't that a greenhouse gas, too?
It is, but the key here is how it's made and used. Conventional carbon capture often requires a lot of energy just to release the captured CO2 from the solvents used to grab it. BICCU effectively replaces that energy-intensive desorption step with this microbial conversion.
Ah, so it lowers the energy cost significantly.
Drastically.
Yeah.
And what's more, these particular methanogens can tolerate contaminants in the CO2 stream that would typically poison traditional chemical catalysts. This makes the whole process much more robust for real-world industrial conditions.
Interesting.
So when you combine BICCU with renewable hydrogen production, green hydrogen, you get a powerful pathway to supply carbon-neutral methane. This can be used as fuel for sectors that are particularly difficult to electrify, like heavy industry or shipping.
Okay, so imagine microbes working as these tiny, robust factories, capturing carbon, converting it into fuel, maybe cleaning up pollution. It's a powerful vision.
It is.
But it's clear that synthetic biology, sort of in its raw form, has immense potential, but also really needs partners to truly flourish if it's going to scale up effectively.
Definitely needs collaboration.
What kind of partner could help coordinate something that complex? Maybe even something that can manage entire energy systems. And that, I think, brings us neatly to artificial intelligence.
Makes sense. AI's role is huge here.
So next we move to AI and its, incredible potential to transform renewable energy systems. This is another area that, even on its own, is already making huge strides in how we generate and distribute power.
Absolutely. AI is already revolutionizing how we handle renewable energy. You know, as Al Nassim's team recently pointed out, the real challenge for renewables has always been their inconsistency.
Right, the intermittency problem.
Mhm.
Sun doesn't always shine, wind doesn't always blow.
Exactly. Historically, renewable systems relied on pretty traditional data analysis, which just lacked the real-time insights into these fluctuations.
Mm.
But AI completely changes that game. It brings advanced predictive analytics, real-time control, and sophisticated optimization.
So AI helps us manage the variability of nature, basically, keep the grid stable. How specifically does it do that?
That's the core of it. AI enables far more accurate forecasting of renewable generation, predicting wind and solar output. That's absolutely crucial for grid stability. Operators can anticipate fluctuations much better.
Better predictions. What else?
Well, beyond just forecasting, AI enhances grid resilience. It improves demand balancing across the network, making sure supply matches demand efficiently. And it facilitates the seamless integration of distributed microgrids, think local solar panels or small wind farms. It also supports intelligent energy storage systems, making sure we store power when it's abundant and release it precisely when needed. Plus, you've got AI contributing to predictive maintenance for energy infrastructure, bolstering cybersecurity, and generally improving smart grid management.
Wow.
These are immense benefits. They significantly bolster our transition to greener energy.
That's a lot of power and control. It really sounds like AI is becoming the super smart conductor of our energy orchestra.
That's a good analogy.
But as AI becomes the central brain for our energy systems, what are the concerns we should be mindful of? Does this kind of power come with its own set of challenges or risks?
It absolutely does. And this brings us to some crucial socio-technical concerns. Researchers like Hinao and colleagues have actually identified 4 major areas we need to watch.
Okay, what are they?
First, there are operational issues. These relate to the reliability and the seamless integration of AI into these already very complex power systems, making sure it actually works smoothly.
Right, no glitches allowed.
Pretty much. Second, and perhaps ironically, there are sustainability concerns. This includes AI's own energy consumption and environmental impacts, a point we definitely need to explore more deeply later.
Ah, the footprint of AI itself. Got it.
Third, there are trust concerns.
Yeah.
This covers things like the transparency of AI decisions. Can we understand why it made a choice? Cybersecurity vulnerabilities, and ensuring fairness in how resources are allocated. Who benefits? Who might lose out?
Fairness is key.
And the fourth.
And finally, there are regulatory and economic issues. Dealing with accountability, who is responsible if an AI makes a mistake, and its overall cost effectiveness. Does the benefit justify the investment? The current research in this area is actually quite fragmented. We lack a cohesive framework to address all these concerns holistically, and there are barriers like large initial investments and the need for really robust data infrastructure, and importantly, persistent concerns about data privacy and potential algorithmic bias. So the smart conductor needs to be reliable, sustainable, fair, transparent, accountable, affordable, a lot to ask, and not accidentally create new problems even as it solves others.
Exactly. It's a complex balancing act.
That's a perfect segue, actually, because as AI becomes more powerful and more deeply integrated into our essential systems, we also have to ask, what's the full cost, both ethically and environmentally? We're starting to see some of the, let's say, unseen burdens.
This is a critical point, and researchers like Viviana Acquaviva and her colleagues really emphasize this in their work. They argue quite strongly that you cannot separate climate AI from broader societal issues, things like resource access, conservation efforts, public health.
They're all interconnected.
Deeply. If AI models are built to address climate issues without considering these human dimensions, they risk actually exacerbating existing inequalities.
Can you give us an example of how that might play out? How could climate AI worsen inequality?
Certainly. One major issue they highlight is data inequities. AI models are trained on data, right? But this data is often unevenly distributed globally.
Meaning more data from some places than others?
Exactly. In practice, this means models tend to perform exceptionally well in data-rich regions, which are often in the global north. But they might fail or perform poorly in data-poor regions, frequently found in the global south.
Ah, so the AI works best where we already have the most information.
Precisely. And this creates a dangerous disparity. It hinders the ability of vulnerable communities to understand, mitigate, and adapt to climate impacts effectively. It essentially widens the global inequalities in our understanding and response to climate change.
Wow. So the very tools meant to help us understand and fight climate change could inadvertently widen the gap between those who have resources and information and those who don't. That's deeply concerning.
It is.
What are some of the proposed solutions then? How do we ensure AI is used fairly and equitably in this space?
Acquaviva and her team advocate for several key solutions. First and foremost, transparency. Transparency in the data sets used, transparency in the algorithms themselves. They also push for explicit documentation of any assumptions made when building the models, and a real commitment to reproducible science so others can check the work.
Open the black box a bit.
Exactly. They also urge researchers to really consider how models perform under distribution shifts. That means testing what happens when conditions change significantly from the data the model was trained on, which is obviously crucial in a rapidly changing climate.
Like testing for unexpected situations.
Right. Furthermore, they encourage designing AI models that are inherently interpretable models that can clearly show how they arrived at a decision. Or, at the very least, provide post hoc explanations, which is basically a way to audit why the AI did what it did after the fact. This helps us diagnose potential biases or issues and understand failures.
So we can learn from mistakes or biases.
Correct. And this isn't just a technical fix, they argue. It's really a call for a cultural shift in academia and industry to actually reward these ethical practices. The bottom line is that ethical considerations and scientific integrity are just deeply intertwined. They have to be integrated into climate science education and the broader discourse.
That makes total sense. And beyond the ethical dimension, the fairness dimension, there's that very tangible environmental cost we mentioned, particularly with the rise of huge models like generative AI. The tools that seem to hold so much promise are also incredibly power hungry.
That's right. And the numbers are quite startling. MIT's 2025 analysis on generative AI's environmental impact really highlights these enormous energy and water demands.
Like how much?
Well, just training a single large generative model like OpenAI's GPT-3 consumed an estimated 12,287 megawatt hours of electricity.
That sounds like a lot. Can you put that in perspective?
Yeah, that's roughly equivalent to the annual electricity consumption of over 100 U.S. homes. And in terms of emissions, it's about 552 tons of CO2, similar to the annual emissions of over 100 gasoline-powered cars.
Wow. And that's just for training one model one time.
Just for training, deployment, running the model, fine-tuning it. That all draws significant ongoing energy as well.
An ongoing drain. That's a pretty sobering thought for a technology we're pinning hopes on to help solve climate change. Are we, being truly honest about this trade-off, or are we just sort of hoping to offset it later?
That's a crucial question we need to grapple with. Data centers, which are the backbone for these AI operations, consume vast amounts of electricity. And critically, also huge amounts of water for cooling.
Right, cooling is a big issue.
It is. And this strains existing infrastructure, power grids, water resources, local ecosystems. Projections are pretty alarming. Some indicate that data center power requirements could double by 2026. They might even rival the electricity consumption of entire countries.
Doubling by 2026, that's incredibly fast growth.
It is. And what makes it worse is that many data centers still rely on diesel generators for backup power or to manage grid fluctuations. This reliance further increases their dependence on fossil fuels. These impacts really call into question the overall sustainability claim of AI and underscore an urgent need for greener computing architectures, much better renewable energy integration for data centers, and frankly, greater accountability from the tech companies driving this.
So we absolutely need to ensure AI, this powerful tool for good, doesn't inadvertently create massive new environmental problems, both in how it's used and how much energy and water it consumes. It's a real double-edged sword that demands very careful stewardship.
Precisely. Very careful indeed.
And speaking of big, bold interventions with potentially huge consequences, let's talk about climate engineering, the idea of directly manipulating Earth's climate. This is where the stakes get incredibly high, and the questions of responsibility are just immense.
Indeed. Climate engineering, or geoengineering as it's often called, encompasses a range of pretty large-scale technological interventions designed to directly alter the Earth's climate system. Ginsky and Oshleys, in their 2024 work, really focus on the critical need for effective control mechanisms, especially for the research phase in this highly sensitive area.
Right. Even just doing the research needs controls.
Absolutely. They remind us that interventions like stratospheric aerosol injection, basically putting reflective particles high in the atmosphere to reflect sunlight back into space, or things like ocean fertilization trying to boost carbon absorption by marine algae, are highly controversial.
Okay, why are they so controversial? What are the big unknowns and the ethical red flags here?
The primary reason is the profound uncertainty. We're uncertain about their actual effectiveness in cooling the planet, and even more critically, there are significant knowledge gaps regarding their potential environmental and societal impacts. We simply don't know enough about the long-term global consequences, the potential side effects.
Unintended consequences on a global scale.
Exactly. Therefore, Ginsky and Oshleys stress that any decision to actually deploy such technologies should only be made once we have sufficient scientific evidence to truly understand the risks versus the potential benefits. And they make another crucial point.
Which is?
Research into climate engineering should not undermine efforts to reduce emissions directly. It cannot be seen as a substitute for decarbonization.
The moral hazard argument.
Precisely. Instead, they argue that developing reliable carbon dioxide removal, or CDR, technologies actually pulling CO2 out of the air is urgent if we're serious about achieving net zero targets. Geoengineering might address symptoms like temperature, but CDR tackles the root cause.
Okay, so it's about being extremely cautious, gathering much more data, and definitely not using it as an excuse to avoid cutting emissions. What kind of oversight do we need for something this potentially world-changing? Who should be in charge of the research?
That's the core of their argument. Ginsky and Ashleys put forward 6 really compelling arguments for why government oversight, and likely international oversight, is absolutely essential, even just for climate engineering research.
Okay, let's hear them.
First, climate policy decisions, including those about research pathways, have incredibly long-term and often irreversible societal implications. These aren't trivial choices.
Right, high stakes.
Second, society needs evidence-based, impartial information to make informed choices, free from, say, commercial interests or undue influence.
Trustworthy information.
Third, the field tests themselves, even small ones, could potentially cause environmental harm, necessitating careful regulation and oversight.
Containing the experiments.
Fourth, governance must cover both public and private research, because private research can often operate with less transparency.
Level playing field for oversight.
Fifth, research agendas themselves can be swayed by funding sources or academic reward systems that may not align perfectly with the broader common good.
Potential biases in research direction.
And finally, private funding sources, specifically, could introduce hidden agendas or biases into the research findings or framing.
Okay, those are really powerful arguments for a strong, independent hand in oversight. Are there any existing models we can maybe learn from, frameworks that tackle this kind of complex international environmental intervention?
There is actually a relevant example, especially for marine geoengineering, the London Protocol.
The London Protocol, what's that?
It's an international treaty that traditionally governs marine pollution, like dumping waste at sea, but it has been amended specifically to regulate marine geoengineering activities.
How does it regulate them?
This framework requires prior assessment and approval for listed techniques, and critically, it mandates measures to ensure that any negative environmental effects are minimized. It serves as a strong model based on precaution, transparency, and public oversight for climate intervention research, at least in the marine context.
Okay, so a precedent exists. This is clearly big, potentially world-changing tech, and it absolutely needs a robust ethical and regulatory compass to guide it. Without that strong oversight, the risks could easily outweigh the potential benefits and create all sorts of unforeseen global problems.
Absolutely. The governance has to keep pace with the science, or even lead it.
All right, finally, in our tour of these individual elements, let's look at something fundamental to our survival. Food. How does genetic precision, like CRISPR, play a role here in our quest for sustainability and in tackling climate challenges?
Food security is just intimately linked with climate change. There's no separating them.
All right.
And genome editing technologies offer incredible promise for building more resilient agricultural systems to face that challenge.
How so?
Well, Feng Shen and co-authors in their 2024 review highlight a pretty stark reality. A growing global population, combined with climate change and dwindling resources like water and arable land, is severely threatening our staple crops.
Things we rely on every day.
Exactly. And traditional breeding methods, even older genetic engineering techniques, they simply can't keep pace with these rapidly evolving challenges. The climate is changing faster than we can breed resistant crops conventionally. This is where CRISPR-Cas systems come in.
CRISPR, that's the powerful, precise gene editing tool we hear so much about, right? How does it specifically help with crops and climate?
Exactly. CRISPR-Cas systems offer incredibly precise genetic modifications. They allow scientists to improve crop resilience, boost yield, and enhance nutritional value with unprecedented accuracy and speed.
More precise than older methods.
Much more. And recent innovations within the CRISPR toolkit, things like prime editing and base editing, have further increased the specificity and efficiency. This means we can make very targeted modifications. For example, enhancing tolerance to what we call abiotic stresses.
Abiotic meaning non-living stresses.
Right. Things like drought, high salinity in soil, extreme heat. Conditions that are becoming more common with climate change. And CRISPR can also enhance tolerance to biotic stresses.
Living stresses, like
Pests and diseases. Imagine making a plant inherently resistant to a specific fungus or insect pest that used to decimate entire harvest without needing chemical pesticides.
So crops can become tougher, more resistant to the changing climate and natural threats like pests and diseases. That alone is huge.
It is, but the benefits go beyond just hardiness.
What else can it do?
Well, CRISPR-Cas can be used to significantly improve photosynthetic efficiency. That means plants can convert sunlight into energy more effectively, potentially leading to higher yields with the same amount of sunlight.
More efficient growth.
Right. It could also enhance nutrient uptake from the soil, so crops might need less fertilizer, which in turn reduces agricultural emissions from fertilizer production and runoff.
Less fertilizer needed, fewer emissions. That's a climate benefit too.
Definitely. And it's not just about hardiness or efficiency. CRISPR can also improve qualities we care about as consumers. Things like taste, texture, shelf life, and even the nutritional content of our food, like boosting vitamin levels.
So better food that lasts longer too. Are there downsides or challenges still?
There are. Challenges remain, like ensuring there are no unintended off-target effects edits elsewhere in the genome, and developing efficient delivery methods to get the CRISPR machinery into the plant cells is still an area of active research for some species.
Okay.
But the review by Chen and his team clearly underscores CRISPR's critical role in addressing both food security and overall agricultural sustainability. In fact, they issue a strong call for its further integration with other cutting-edge fields like nanotechnology, synthetic biology, and machine learning to develop what they envision as the next generation of crops.
So imagine crops that practically grow themselves, are resistant to disease, thrive in harsher conditions, all while being more nutritious and needing fewer inputs like water and fertilizer. Genetic editing is bringing us closer to that reality.
It really is.
It transforms agriculture from just a sector we need to make less damaging into potentially a powerful part of our climate solution toolkit. It's clear that each of these technologies, synthetic biology, AI, climate engineering, CRISPR in their raw form, has immense potential, but also clear limitations.
Exactly. Each field alone, as powerful as it is, cannot fully address the truly complex, interconnected challenges of climate change, energy transition, and food security. They bump up against their own limits.
Which raises that important question you posed earlier.
Right. How do these disparate pieces, when we start looking at them through a synthetic lens, through this idea of carbon alchemy, begin to form not just a solution, but a coherent, holistic solution?
That's where the real magic happens, perhaps.
That's where the transformative power lies, in the connections.
Okay, now we enter the synergy forge. This is the alchemical crucible where these ideas transmute and recombine. This is where it gets really interesting, I think.
Me too. This is the exciting part.
You can think of it like an architect designing a multi-story building, where each domain we've discussed is like a structural pillar. It provides essential support, but it also has to interact correctly with the other pillars and floors to make the whole building stand strong.
That's a good way to put it. Or like a symphony orchestra.
Oh, I like that. Explain.
Well, you have different sections: strings, woodwinds, brass, percussion. Each is powerful on its own, but it's when they play together, following the conductor's score, that you get this rich, complex, coherent piece of music that's far more impactful than any solo instrument could be.
Right. The synergy creates something greater.
Exactly. And this stage, this synergy forge, is absolutely crucial because it's about moving beyond just, say, additive innovation, just sticking things together to truly transformative connections.
Deeper integration.
Yes. And here, we have to consciously consider the complex ecological feedback loops, what happens downstream when we combine these things. And the ethical implications need to be front and center at every single turn. The goal isn't just cool tech. It's to create inventions that genuinely harmonize technology with ecology and society.
Okay, let's start forging then. Let's bring together those tiny biological engineers we talked about, the microbes, with the immense processing power and learning capability of AI. What happens when we really synthesize synthetic biology and artificial intelligence?
This combination creates an incredibly fertile ground for novel climate solutions. It does this by establishing what we can call a cyber-biological loop.
A cyber-biological loop. Explain that.
Okay, so synthetic biology already uses these iterative cycles: design, build, test, learn. You design a genetic circuit, build it in an organism, test how it works, learn from the results, and then refine the design.
Right, an engineering cycle.
That cycle actually mirrors how machine learning operates, learning from data to improve performance. Now, imagine integrating biological sensors, maybe engineered microbes themselves, with Internet of Things, IoT devices. These sensors provide real-time data on environmental conditions, say the concentration of a pollutant or the level of CO2 in the air or water.
Okay, real-time biological data.
AI algorithms can then analyze this constant stream of data instantly, They could predict, for example, an upcoming spike in pollution based on subtle environmental cues, or they could optimize the metabolic pathways of the engineered microbes in that environment
How would AI optimize metabolism?
by dynamically adjusting their behavior in real time. Maybe by sending signals that trigger the expression of certain genes or enzymes only when needed, making them more efficient or responsive.
So AI becomes the intelligent director, the conductor of these microbial factories. It sounds powerful, but does giving AI this kind of control over living organisms raise any, red flags? What are the biggest ethical questions that come up when we talk about a cyberbiological loop?
That's a critical question, and yes, it raises significant ethical considerations that would need careful attention at every stage. Questions around autonomy, how much control does the AI have versus the organism or human oversight? Safety, what happens if the AI makes a mistake or the system goes wrong? Containment, how do we ensure these AI-controlled organisms stay where they're supposed to? And accountability, who is responsible? These ethical guardrails would be paramount.
Okay, so acknowledging the ethics is step one, but assuming we navigate that, give me a concrete example of this loop in action.
Sure, imagine engineered microbes designed to convert CO2 into bioplastics, or maybe methane fuel. These microbes could be embedded with AI-enabled control systems. These systems could then modulate the expression of specific enzymes within the microbes in real time, maybe based on the availability of sunlight for energy or the current market demand for the bioplastic.
Adapting production on the fly.
Exactly. Or machine learning models could be trained on vast data sets to identify which specific genetic circuits lead to the highest carbon sequestration rates under different varying environmental conditions, temperature, nutrient availability, etc. This allows for continuous optimization over time.
Okay, that's AI enhancing biology. Does this synergy work in reverse too? Can synthetic biology actually help AI become more sustainable, addressing that big carbon footprint we discussed?
Absolutely. And this is where the reverse synergy gets really exciting. Remember the biointegrated carbon capture and utilization, or BICCU, systems we talked about?
Yeah, the archaea making methane from CO2 and green hydrogen.
Right. Now imagine if the green hydrogen needed for that process is supplied by renewable energy systems, wind, solar, whose output is being optimized by AI for maximum efficiency and lowest cost.
Okay, AI optimizing the clean energy input.
And then the methane produced by the BICCU microbes is used to power the very data centers running the AI that's optimizing the hydrogen production.
Whoa.
You see the loop. AI helps make clean hydrogen, which microbes use to eat CO2, and make clean fuel, which powers the AI. In this way, AI and synthetic biology form a virtuous cyberbiological loop, optimizing each other's performance and potentially significantly reducing their collective environmental footprint.
Imagine tiny, smart microbes working in perfect sync, directed by AI to capture carbon or create sustainable fuels, maybe even powering the AI itself. It's like a miniature, self-optimizing, sustainable technological ecosystem.
That's the vision. It's truly compelling.
It really is. Okay, so we've seen how AI and biology can potentially work together beautifully. But as we establish, AI comes with its own set of serious concerns, especially around fairness, transparency, and its substantial environmental footprint. How do we integrate ethical considerations into AI for renewable energy specifically to build trust in this green transition?
This is about intentionally weaving those ethical guidelines we discussed earlier directly into the fabric of AI systems used for energy. It's not an add-on, it has to be integral.
So how do we do that? What are the practical steps?
The solutions really start with transparency. Renewable energy companies, grid operators, they need to adopt transparent data practices. That means openly sharing, where feasible and safe, the data sets and algorithms they use for things like forecasting electricity demand or controlling grid flow.
So not just saying, trust our magic AI, but actually showing the work, showing the data.
Exactly. That builds trust and allows for external scrutiny and verification. Beyond just transparency, it's critical to rigorously assess these AI models under those distribution shifts we mentioned.
Testing for when conditions change unexpectedly.
Right. This means deliberately testing how well the models perform when climate-induced weather variability, like unprecedented heat waves or storms, causes conditions to deviate significantly from what the AI was initially trained on. This ensures the models remain robust and reliable in our actually changing climate, not just in historical simulations.
That seems vital for climate-related AI.
It is. And we should also prioritize using AI models that are inherently interpretable, the ones that can clearly show how they arrived at a decision. Or, if we must use more complex black box models like deep learning for performance reasons, We need robust methods for post hoc explanations, ways to audit why the AI did what it did after the fact.
Hmm.
This is crucial for diagnosing potential biases and understanding failure modes.
Understanding the why behind the AI's actions.
Yes, and another absolutely crucial aspect is global equity. The energy transition, which is increasingly being driven by AI, must not exacerbate existing global inequalities.
How do we ensure that?
It means ensuring AI models are trained on diverse data, representing conditions and needs from both the global north and the global south. Solutions must be applicable and beneficial worldwide, not just optimized for data-rich regions. This requires active collaboration with local communities in different parts of the world, respecting local knowledge, and implementing robust regulatory oversight to guarantee fairness and prevent new forms of technological dependence.
So fairness baked in from the start.
Right. This ethical integration isn't just about mitigating potential harm, it fundamentally builds public trust, which is absolutely vital for the widespread adoption and ultimate success of AI-enabled renewable energy systems. People need to trust the systems managing their power.
It's about building an AI system for energy that's not just smart, but also demonstrably fair, transparent, accountable, and resilient to climate change itself, making sure the benefits are distributed equitably across the entire globe.
That's the goal, a just transition, enabled by ethical AI.
Okay, let's connect another couple of threads. Let's link our genetically precise agriculture, the CRISPR crops, to the broader energy and carbon systems. How can these advanced crops play a role not just in feeding us more efficiently, but also in climate mitigation and maybe even energy?
This is where we start to really envision what you might call smart agroecosystems. We know CRISPR-edited crops are being designed to enhance food security, that's a primary driver, but their impact can extend far beyond just the plate.
How so?
Well, remember we talked about improving photosynthetic efficiency and nutrient uptake.
Yeah, needing less fertilizer and water.
Right. That directly translates to a significant reduction in agricultural emissions. Fertilizer production is very energy intensive, often relying on natural gas. And pumping water for irrigation uses a lot of energy too. So more efficient crops mean lower embedded energy use and lower direct emissions from things like nitrous oxide from fertilizers.
Okay, so the crops themselves become part of the climate solution just by being inherently more efficient resource users.
Precisely. But we can potentially take it much further than just efficiency gains. Crops could be engineered for enhanced root systems, deeper roots, more extensive root networks.
Why is that important?
Deeper, bigger root systems can sequester significantly more carbon directly into the soil. The roots themselves are made of carbon, and they also exude carbon compounds that feed soil microbes. Healthier roots mean more stable soil carbon. These enhanced root systems could even actively stimulate beneficial soil microbes to fix more carbon, turning agricultural land into a much more effective carbon sink than it is today.
Turning farms into carbon sinks. Now that's interesting.
And now, bring in the synergy with other fields. Imagine combining CRISPR crop development with engineering biology for soil microbes.
How would that work?
You could have microbes specifically engineered to fix atmospheric CO2 very efficiently in the soil, perhaps converting it into stable organic carbon compounds. These microbes could then supply some of that organic carbon directly to the roots of the crops. Simultaneously, you could use CRISPR to modify the plants themselves to interact better with these specific carbon-fixing microbes, maybe signaling them or providing specific nutrients they need.
Creating a designed symbiotic relationship for carbon capture.
Exactly. A true partnership engineered for maximum carbon drawdown in an agricultural setting.
And where does AI fit into this advanced agricultural picture? Could it manage this complex system?
Absolutely. AI models could play a powerful predictive role. They could analyze future climate projections for a specific region and help identify the optimal gene edits needed in crops to maximize both yield and carbon sequestration under those predicted future conditions.
Tailoring crops to future climates.
Yes. Furthermore, imagine IoT sensors deployed across these fields, continuously monitoring everything: soil moisture, nutrient levels, microbial activity, actual carbon content in the soil, crop health via spectral imaging.
A data-rich farm.
Extremely data-rich.
Yeah.
All this data would feed into AI platforms. These platforms would then create a dynamic, smart agroecosystem. They could optimize everything in near real-time precision irrigation, targeted nutrient delivery, maybe even suggesting optimal planting densities or harvest times, all while maximizing carbon storage.
Wow. We're talking about a farm where the plants themselves are designed to be carbon sinks. They need fewer resources, and AI helps them thrive in perfect sync with beneficial microbes. It really makes agriculture a central part of the climate solution, not just, a sector we need to decarbonize.
That's the potential shift in thinking. Agriculture as a climate solution engine. It's a profound change.
It really is.
Yeah.
Okay, let's pivot back to climate engineering for a moment. We talked about the grand interventions, but also the serious controversies and uncertainties. How do we bring synthetic biology and AI into the fold here, perhaps to harmonize climate engineering efforts and ensure they are more targeted and responsible?
This is about addressing the valid concerns about the scale and potential unintended consequences of large-scale geoengineering. We can use synergy to develop more intermediate, arguably more ecologically sound approaches. These approaches could then be enhanced by synthetic biology and, crucially, governed carefully by AI.
So not necessarily planet-wide interventions, but something more nuanced?
Exactly. Instead of focusing solely on massive global interventions like stratospheric aerosol injection, which carry huge unknowns, we could concentrate more on enhancing natural ecosystem technologies.
Like what?
This means restoring and amplifying natural carbon drawdown mechanisms. Think about restoring wetlands, mangrove forests, kelp forests. These ecosystems are incredibly efficient at naturally sequestering large amounts of carbon.
So step one is working with nature, helping it do its job better, rather than trying to overpower it.
Precisely. That's the starting point. And then synthetic biology could potentially come in to dramatically accelerate or enhance these natural processes in targeted ways. How?
Give me an example.
Okay, imagine engineering specific organisms, maybe bacteria or cyanobacteria, to produce sticky, long-lasting polysaccharides, complex sugar molecules.
Sticky sugars. Why?
These substances could promote the aggregation of organic matter in the ocean, including carbon fixed by phytoplankton. This would create heavier particles, sometimes called carbonaceous marine snow, that sink more rapidly to the deep ocean floor. This effectively sequesters that carbon long-term, removing it from the active carbon cycle for potentially centuries or millennia.
Huh. Using engineered microbes to help carbon sink faster. That's a targeted, biologically amplified approach to carbon drawdown.
Exactly. It's working with a natural process, but giving it a boost where appropriate and safe. However, and this is critical as Ginsky and Ashley strongly emphasize in their work on governance, any such intervention, even these more ecologically integrated ones using synthetic biology, must be incredibly carefully governed. Field trials must be limited in scale and duration, highly transparent, and subject to rigorous international agreements and oversight, perhaps building on frameworks like the London Protocol we mentioned earlier.
Precaution is paramount. And how does AI provide that crucial oversight in this scenario?
AI can play a pivotal role in the governance and monitoring aspect. Imagine deploying drones, autonomous underwater vehicles, or using satellite imagery, all equipped with advanced sensors. These could feed a continuous stream of environmental data, water chemistry, biological activity, currents into AI systems.
Real-time monitoring on a large scale.
Yes. And the AI could then detect any unintended ecological impacts, like effects on non-target species or changes in nutrient cycles, far more rapidly and comprehensively than human observation alone could manage.
An early warning system.
Exactly. AI can also provide sophisticated decision support systems. These systems could help policymakers and scientists weigh the complex, multidimensional risks and benefits of any proposed intervention based on real-time data and predictive modeling. This synergy between synthetic biology for enhancement, AI for monitoring and decision support, and robust regulatory frameworks creates a vital feedback loop. It helps ensure that interventions are not only potentially effective, but critically are implemented in an ethically sound and environmentally responsible manner.
It's about smart, targeted ecological repair or enhancement, amplified by biology, but constantly watched over and guided by AI, ensuring we don't accidentally cause more harm than good. It sounds like a truly sophisticated, adaptive approach to climate intervention, much more nuanced than just spraying particles into the sky.
That's the idea, adaptive management informed by data and ethics.
Okay, we've just explored how AI can help with climate solutions, monitoring ecosystems, optimizing energy. But earlier, we hit on its own massive carbon footprint, the huge energy and water demands of those data centers. How do we square that circle? Can we realistically address AI's carbon footprint, maybe through bioenergy integration, to create that virtuous cycle you hinted at?
This is one of the most exciting potential convergences, I think. Because yes, the current problem is stark. Data centers consume enormous amounts of electricity and water. It's a huge sustainability challenge for the tech industry.
Right.
But AI itself can be part of the solution to its own impact. There are already efforts underway, for example, using AI algorithms to schedule computationally intensive tasks.
How does scheduling help?
The AI can schedule tasks to run specifically during periods when renewable energy on the grid is abundant and cheap, like midday for solar or windy nights for wind power. Or can even shift workloads geographically, moving computations to data centers in regions that currently have a surplus of clean power.
So AI becomes smart about when and where it does its heavy lifting to minimize its reliance on fossil fuels.
That's the first step, using AI for operational efficiency. But for a truly radical synergistic integration, we could look at directly powering AI infrastructure using bioenergy systems.
Okay, tell me more about that.
Remember the BICCU concept from Seaborg and colleagues? The methanogenic archaea converting captured CO2 and green hydrogen into methane?
Yes, the microbes making fuel from CO2.
Imagine taking the methane produced by those microbial bioreactors and using it to fuel highly efficient microturbines or solid oxide fuel cells that are located right at the data center. They generate electricity on site to power the servers running the AI.
Decentralized bio-based power for the data center.
Exactly. And here's where the virtuous cycle really kicks in beautifully. Data centers generate a massive amount of waste heat from all the servers running.
Right, they need huge cooling systems.
What if, instead of just venting that heat or using more energy to cool it, we capture that waste heat and use it to maintain the optimal temperatures needed for the microbial bioreactors to operate at peak efficiency? Many biological processes, including methane production by these archaea, work best within specific temperature ranges.
Whoa, so it becomes a truly closed-loop system. The carbon captured by the microbes fuels the computing infrastructure. The waste heat from the computers helps the microbes capture more carbon, which then fuels the computers. That's genuinely circular.
Exactly. It's a perfect example of industrial symbiosis, mimicking how natural ecosystems work, where the waste product of one process becomes a vital resource for another. AI could even be used to optimize this heat exchange and the entire integrated system.
That's amazing. Are there other angles to this bio-AI synergy for sustainability?
We could even extend this concept to the hardware itself. Imagine using synthetic biology techniques to produce biodegradable or bio-based materials. These materials could then be used to manufacture components for AI hardware, things like circuit boards or casings. This would significantly reduce the ecological footprint associated with manufacturing the electronics in the first place and deal with the growing problem of electronic waste.
Wow, biodegradable computer chips almost.
It's moving in that direction. Such designs would echo natural ecological cycles, creating a truly sustainable technological infrastructure from cradle to grave.
Imagine AI systems literally fueling themselves by eating CO2, their waste heat helping the process, and even their physical hardware being biodegradable or bio-based. That's not just a virtuous cycle, that's a complete reimagining of our technological relationship with the planet.
It represents a fundamental shift towards integrating technology within ecological boundaries.
Okay, this has been incredible, exploring these technological syntheses. But as we've touched upon repeatedly, and rightly so, technology cannot be divorced from ethics. It's woven through every aspect we've discussed. So how do we systematically build in ethical and societal synergies? How do we embed values into innovation from the very start, not just as an afterthought?
This is perhaps the most fundamental point of the entire Synergy Forge,
Yeah.
and maybe the whole concept of carbon alchemy. It's non-negotiable. We absolutely have to embed ethical considerations at every single stage of integration and development.
So it's foundational, not just a checkbox.
Foundational. We've seen principles emerging from the research we discussed. Ginsky and Oshleys advocating for strong public oversight and precaution in climate engineering. Aquaviva and her team stressing fairness, transparency, and inclusive data practices in climate AI. Chen and his team highlighting the need for responsible governance of genome editing in agriculture.
Right, these threads kept coming up.
Together, these guidelines coalesce around a set of key principles: transparency, inclusivity, equity, accountability, and precaution. By consciously adopting and embedding these principles into the innovation process itself, we work towards preventing our powerful inventions from becoming, a Pandora's box, and instead guide them towards being more like the Philosopher's Stone, transformative in a positive way.
I like that analogy. So what do these principles look like in practical steps? How do we put them into action on the ground?
Okay, practically, this could mean creating things like citizen science platforms. These platforms could enable local communities to participate directly in monitoring, say, the environmental effects of engineered microbes deployed in their area, or perhaps evaluating the accuracy and fairness of AI-driven resource forecasts.
Yeah.
This fosters trust, transparency, and a sense of shared ownership.
Getting people involved directly.
Yes. We should also establish more regulatory sandboxes. These are controlled environments where novel technologies, like AI-managed energy grids or CRISPR-enhanced ecosystems, can be tested under rigorous oversight and with clear boundaries before any consideration of widespread deployment. It allows learning in a safe space.
Testing grounds with guardrails.
Exactly. Education is also absolutely critical. University curricula and professional training must teach not only the technical aspects of synthetic biology, AI, genetics, and climate science, but equally important, their complex ethical, legal, and social dimensions, the ELSI aspects.
Training ethically aware innovators.
Precisely. This holistic approach helps ensure that the next generation of scientists, engineers, and policymakers is not just technically brilliant, but also ethically informed and socially responsible. They need to understand the societal context of their work.
This isn't just about building amazing tech, but building it right. Building it with communities, building it with ethical frameworks baked in from the start, and always keeping an eye on the long-term impacts and potential unintended consequences. The question isn't just, can we build this, but should we? And if so, how do we do it responsibly and equitably?
That's the heart of it. Responsible innovation has to be the standard.
Okay. Now that we've forged these connections in the Synergy Forge, explored these incredible potential integrations, let's look at some concrete examples. Let's sketch out some prototype blueprints, if you will. These range from the perhaps immediately achievable to the truly visionary. This is where we can really see invention alchemy in action, bringing these synthesized concepts to life.
Right. These blueprints offer more tangible pathways. Each one is designed to build upon the peer-reviewed mechanisms we've discussed and tries to align with the ethical considerations that are so important. They really illustrate the incredible spectrum of possibility when we purposefully synthesize these distinct fields.
Let's start with what feels like the most achievable, the most grounded example, the symbiotic carbon farm. What does this conservative prototype look like in practice? How would it actually function?
Okay, the symbiotic carbon farm is essentially an integrated agricultural system. Its primary goal is to maximize carbon sequestration in the soil while simultaneously producing food efficiently. It combines three core elements we've touched on.
All right, element one.
First, you'd use CRISPR-edited crops. These crops would be specifically developed for traits like enhanced root depth, getting carbon deeper into the soil, improved nitrogen use efficiency, so less fertilizer is needed, and maybe optimized photosynthetic performance. These are traits that researchers like Chen and his colleagues have shown are feasible targets for genetic editing.
Okay, smarter, more efficient crops.
Yeah.
Element two.
Second, you'd introduce engineered soil microbes into the system. These microbes would be designed, perhaps drawing on work like Lee Smith's team described, to actively fix atmospheric CO2 into stable organic acids within the soil. They might also be engineered to secrete beneficial compounds like biosurfactants, which can improve soil structure and water retention.
So microbes actively building healthy, carbon-rich soil. And the third
So
element...
the third element is the digital layer. You'd have IoT sensors deployed throughout the fields, continuously monitoring critical environmental parameters, soil moisture, nutrient levels, maybe even direct measurements of soil carbon content in real time. This data feeds into AI algorithms.
And the AI does what?
The AI algorithms analyze all this incoming data, integrate it with weather forecasts, and then precisely predict optimal schedules for things like irrigation and fertilization. But here's the key difference. The optimization isn't just for maximizing crop yield. It's explicitly tailored to also meet specific carbon sequestration goals for that farm.
Ah, so it's managing the farm for both food and carbon capture. It's a highly intelligent farm that not only grows food, but is actively managed to remove carbon from the atmosphere.
That's the concept.
What's the expected impact of something like this? And how quickly could we realistically see this becoming widespread? Is it near term?
The purpose, as we said, is maximizing soil carbon while producing food. The enhanced roots and microbial activity dramatically increase carbon deposition and stability in the soil. Meanwhile, the optimized irrigation and nitrogen use reduce water waste and lower agricultural emissions, like nitrous oxide. And crucially, such a farm also generates verifiable data on its carbon sequestration performance.
The data for it.
Data that could potentially be used for carbon credits, creating new revenue streams for farmers who adopt these practices. In terms of timeline, this prototype builds on existing, rapidly advancing technologies. CRISPR in crops is moving fast, soil microbiome engineering is progressing, and precision agriculture using sensors and AI is already established. So realistically, we could see versions of this being implemented within the next 5, maybe 10 years.
5 to 10 years. That's quite near term.
Relatively, yes. It offers incremental but meaningful climate mitigation, significantly improves soil health, which has its own benefits for resilience and water quality, and enhances crop resilience to stresses like drought and heat. In terms of cost, initial setup for a mid-sized farm might be in the tens of thousands of dollars for the sensors, AI platform subscription, and microbial inoculants. That's potentially accessible, especially with support from climate-smart agriculture grants or income from carbon credits.
That sounds fantastic. A smart farm producing food, fighting climate change, potentially profitable for farmers. But what are the challenges, the ethical considerations we need to keep in mind for something like this?
There are definitely significant challenges. Regulatory approval for genetically edited crops is still a complex landscape, varying by country. Public acceptance of both GMOs and AI in food production can also vary greatly, depending on the region and how clearly the benefits and safeguards are communicated.
Trust and transparency are key there.
Absolutely. Then there are biosecurity concerns. We need rigorous protocols to ensure any engineered microbial modifications don't escape and have unintended consequences in surrounding ecosystems. Containment and monitoring are vital.
Then ethically,
Any deployment must involve local communities from the outset, ensuring their concerns are heard and addressed. Especially if implemented in developing regions, it must rigorously respect data sovereignty, who owns the farm data, and avoid exploiting local knowledge or resources. Benefits need to be shared equitably.
Okay, so a very real-world example we might see relatively soon are food potentially growing in smarter carbon-capturing farms. But it needs careful rollout, focusing on safety, transparency, and community engagement.
Precisely. Cautious optimism is probably the right stance.
Now, let's venture into something a bit more speculative, maybe further down the road. The bio-AI carbon cloud. This sounds incredibly futuristic. What exactly does this prototype entail?
Okay, the bio-AI carbon cloud envisions a distributed network of highly specialized bioreactors. And crucially, these bioreactors would be co-located directly with data centers.
Bioreactors next to data centers. Why?
Inside each bioreactor unit, you'd have those methanogenic archaea we discussed earlier, specifically engineered perhaps for even higher efficiency. They'd be converting captured CO2, maybe piped in from an industrial source, or eventually from direct air capture along with green hydrogen, into methane. This is the BICCU concept from Seaborg and colleagues again, chosen because it lowers the energy penalty of capture.
Okay, microbes making methane at the data center, then what?
The methane produced by these microbes then directly fuels high-efficiency microturbines or perhaps solid oxide fuel cells, which are also located right there on site. These generate electricity to power the servers in the co-located data center.
So the data center is effectively powering itself by feeding on CO2. And you mentioned that heat exchange loop earlier.
Exactly. That's the elegant part. The waste heat generated by the data center servers, instead of being vented, is captured and used to maintain the optimal warm temperature that the methanogenic archaea need to function at peak efficiency.
So the data center powers itself, and its waste heat helps the CO2-eating microbes make more power for it. That's a perfect, almost symbiotic loop.
That's the core idea. A closed-loop system creating a powerful synergy. And AI algorithms would play a critical scheduling role here too.
Wow.
The AI could match the data center's computational workloads, which can vary a lot to the bioreactor's current energy production rate. Maybe shifting less critical tasks to times when biogas output is higher, or distributing workloads across different linked data centers in the network based on local bioenergy availability.
Fine-tuning the whole integrated system.
Right. And a network of sensors would continuously monitor everything. The flow of CO2, the health and productivity of the microbes in the reactor, the energy demand of the servers, the methane output. All this real-time data feeds into machine learning models that continuously optimize the entire process, maybe adjusting nutrient feed rates to the microbes or fine-tuning enzyme expression for maximum efficiency.
What's the big picture purpose of this kind of system, and what impact could it really have if it works?
The primary purpose is to directly and significantly address AI's substantial carbon footprint. It does this by creating a truly symbiotic relationship between computation and carbon capture. Captured CO2 is literally converted into energy that powers the AI systems, and the AI itself helps optimize the carbon capture process.
A self-decarbonizing AI system.
Essentially, yes. Any surplus methane produced beyond the data center's immediate needs could potentially be injected into the existing natural gas grid, or used for heating nearby buildings, creating additional value and displacing fossil fuels. The potential impact is significant. It could meaningfully reduce the carbon intensity of large computing facilities and provide a scalable model for decarbonizing the rapidly growing data center industry globally. It would also really push the boundaries of microbial engineering and AI integration.
What about cost and feasibility for this one?
Building a pilot installation would likely cost in the range of, say, $3 million to $5 million. That makes it feasible for well-funded institutional labs, large energy companies looking for decarbonization solutions, or perhaps ambitious venture-backed startups focused on green computing.
But something this complex and cutting edge must come with its own set of risks and governance challenges, right?
Absolutely. The risks include potential biosecurity concerns, like the accidental release of these engineered archaea, although likely easier to contain in an industrial setting than a farm. There's also the inherent technical complexity of integrating these diverse biological, chemical, and digital systems smoothly and reliably. And economic viability is still a major hurdle. It would require further advancements in things like direct air capture technology, cheaper green hydrogen production, and more efficient bioreactor engineering to become fully cost competitive with grid power, even dirty grid power.
And governance.
Governance would be needed. Frameworks like the London Protocol, even though designed for marine environments, could provide valuable insights into principles for regulating the contained deployment of such engineered biological systems. Transparent reporting of performance metrics, energy use, and any environmental releases would also be absolutely critical for building public trust and ensuring accountability.
Okay. Imagine your online searches, your cloud storage, your AI interactions, all powered by data centers that are literally breathing in CO2 and turning it into their own energy. That's a powerful step towards closing the loop on AI's environmental impact. It's speculative, but you can see the logic.
The internal logic is strong. Yes, a very interesting possibility.
All right, let's push the boundaries even further now. We've gone from a smart farm to a carbon-eating data center. Let's move to the truly visionary prototype, the Planetary Symphony and AI-governed ecosystem network. This genuinely sounds like something out of a science fiction novel. What's the mechanism behind this grand, almost audacious vision?
This is truly a North Star vision. It conceives of the Earth itself, or at least large parts of its biosphere, as a dynamically managed, potentially self-regulating system, orchestrated for climate stability and ecological health.
Okay, how?
The Planetary Symphony envisions a global, interconnected network of engineered and enhanced ecosystems, both terrestrial and marine. These ecosystems would be continuously monitored and orchestrated by a sophisticated, globally integrated AI system.
Engineered ecosystems, like what?
On land, you might see vast reforested areas using CRISPR-edited trees designed for faster growth, deeper roots, and enhanced carbon sequestration, maybe even enhanced fire resistance. You'd have agricultural lands operating like the symbiotic carbon farms we discussed, but integrated into a larger network. Engineered soil microbes designed for carbon fixation might be deployed strategically in degraded lands.
And in the oceans?
In the oceans, perhaps engineered phytoplankton or microbes could be introduced in specific, carefully chosen zones to boost carbon fixation rates and maybe enhance the formation of that sinking organic marine snow we talked about, drawing carbon down to the deep sea. The key is, it wouldn't be one single intervention, but a network of diverse interacting interventions.
How on earth would we monitor and manage something on that planetary scale? That sounds like a monumental, almost impossible task.
That's where the digital nervous system comes in. You'd need a constellation of satellites, fleets of autonomous drones, ocean buoys, ground sensors, all equipped with advanced multispectral sensors and communication capabilities. They would provide a continuous, real-time stream of data on the health and status of these ecosystems across the entire planet. Carbon fluxes, biodiversity indicators, water cycles, everything.
An Earth-scale monitoring network, and this data feeds.
This immense planetary-scale data set would feed into a global AI infrastructure. Ideally, this AI infrastructure itself would be powered sustainably, perhaps using our bio-AI carbon cloud concept to ensure its own operations are clean.
Okay, so a clean AI managing the planet's ecosystems. What does the AI do with all that data?
This global AI would integrate all the incoming data, run complex predictive models simulating Earth systems under various climate scenarios, and then this is the crucial part, potentially issue coordinated instructions or recommendations for interventions across the network.
Like what kind of instructions?
For example, it might suggest adjusting irrigation patterns in a large agricultural region based on drought forecasts and soil carbon goals, or recommending the deployment of more carbon-fixing microbes in a specific oceanic patch showing nutrient availability, or scheduling biomass harvests from engineered forests for bioenergy use, or critically, pausing certain interventions automatically if adverse or unexpected ecological effects are detected by the monitoring system.
So it's an adaptive management system on a global scale.
Exactly. The system would likely employ multi-objective optimization. It wouldn't just be optimizing for carbon drawdown. It would have to balance that primary goal with other crucial objectives, like conserving biodiversity, ensuring food production isn't compromised, maintaining water resources, and promoting socioeconomic equity across different regions.
This sounds like actively managing Earth's vital signs, trying to maintain planetary health. It's an incredibly ambitious undertaking. What would be the ultimate purpose and potential impact if such a system could ever be realized?
The ultimate purpose is to actively manage Earth's carbon cycle while rigorously respecting ecological integrity and social justice. Instead of relying on maybe single blunt force geoengineering interventions with potentially catastrophic side effects, the planetary symphony treats the biosphere more like that dynamic orchestra we mentioned earlier. Each component, from an engineered microbe to a vast managed forest, is carefully tuned and coordinated by the AI conductor to achieve a harmonious global balance.
And governance. Who controls the conductor?
Governance would have to be absolutely embedded into the system's design from day one. Ideally, all the core algorithms, the data inputs, and any proposed large-scale interventions would need to be publicly accessible and transparent. Decisions couldn't be made solely by the AI. They'd likely need ratification by an international council representing diverse stakeholders from all around the world: scientists, policymakers, indigenous groups, civil society. Trust and legitimacy would be paramount.
That governance structure sounds almost as complex as the technology itself.
It might be even more complex. The potential impact, though, if achievable, is truly transformative. It could revolutionize climate mitigation, potentially help achieve stable net negative emissions at a planetary scale, actively restore degraded ecosystems, and bolster global food security in the face of climate change. But the cost?
Billions.
Trillions. Likely billions, perhaps trillions of dollars invested over decades. It would necessitate unprecedented international collaboration, massive public-private partnerships, dedicated global climate funds. Though perhaps low-cost citizen science kits could involve the public in monitoring parts of the system.
The potential impact is immense, almost utopian sounding, but I imagine it also raises incredibly profound ethical questions about control, hubris, unforeseen consequences.
It absolutely does, and these are questions we cannot brush aside. Who ultimately controls such a powerful planetary AI? Whose values and priorities guide its optimization algorithms? How do we prevent unintended ecological homogenization, where we optimize for carbon but lose biodiversity? How do we guard against unforeseen, cascading side effects on a global scale? The sheer complexity and the potential for irreversible mistakes mean that such a system would require decades, maybe centuries, of dedicated research, extensive global public deliberation, and extremely cautious, iterative testing in contained environments first.
It's definitely a North Star, then, something that pushes the boundaries of what we can even conceive of.
Precisely. It inspires both immense caution about our technological power and, at the same time, an audacious aspiration about what might be possible if we could truly learn to manage our relationship with the planet wisely.
This is the ultimate vision. Perhaps Earth itself is a complex, self-regulating, perhaps partially engineered system, managed for its own health and, by extension, ours. A true North Star for what integrated ethical technology could strive towards.
It's a lot to take in.
It is. Okay, these prototypes are exciting, maybe a little terrifying in the case of the last one. They paint pictures of incredible potential. But as any good alchemist knows, or any good engineer or scientist for that matter, the real work isn't just in the vision, but in the practicalities.
Right. Grounding the vision.
What does it actually take to make these ideas a reality? What are the budgets, the ethical guardrails we absolutely need, and the cold, hard, real-world feasibility?
And this raises that important question. How do we ensure these potentially transformative inventions are not only technically brilliant, but also ethically sound, socially accepted, and economically viable enough for widespread, equitable benefit? It's about grounding the aspiration in the messy reality of implementation.
Let's start with a realistic look at the materials and costs for these prototypes. We touched on them briefly as we went, but can you give us a kind of consolidated view on the funding needed?
Certainly. So just to recap the rough scales, the symbiotic carbon farm, our conservative prototype, we estimated in the range of tens of thousands of dollars for a typical mid-sized farm setup. Relatively accessible.
Okay.
The bio-AI carbon cloud, our more speculative prototype for a pilot installation next to a data center, we estimated would be in the millions of dollars range, maybe $3 to $5 million to start. That puts it in the realm of institutional labs, large corporations, or well-funded startups.
Right.
And the Planetary Symphony, our visionary prototype,
Right.
well, that would clearly require investment on a completely different scale. Billions, likely trillions of dollars, phased over decades of development and deployment.
So vastly different scales. How do the funding pathways differ for each?
They'd have to. For the symbiotic carbon farm, you're looking at funding sources like existing climate-smart agriculture grants, maybe subsidies for soil health practices, and importantly, the potential revenue from emerging carbon credit markets or schemes rewarding carbon farming.
Using existing mechanisms, mostly.
Yes. For the bio-AI carbon cloud, funding would more likely come from institutional research budgets, corporate R&D from large energy or tech companies looking to decarbonize their operations, and potentially significant venture capital investment targeting deep tech and climate solutions.
Okay. And the Planetary Symphony, where does that kind of money come from?
That scale requires something different. It would necessitate sustained, long-term international public-private partnerships. Think major government commitments pooled together, perhaps channeled through dedicated global climate funds, maybe analogous to vaccine development funds or space exploration collaborations. It's beyond any single entity.
A global effort for a global system.
Precisely. But it's also important to emphasize, especially for the farm and data center prototypes, that modular design and eventual economies of scale could significantly reduce the per-unit costs over time as these technologies mature and are deployed more widely. The first ones are always the most expensive.
Right. So it's not just about the initial scientific breakthroughs. It's about smart investment strategies, supportive policy, and viable funding models that can support this kind of long-term, high-impact innovation across different scales.
Exactly. The economics have to work or be made to work through policy.
Okay, beyond the money, which is always a factor, the ethical and governance challenges feel absolutely paramount, especially as the scale increases. How do we prevent these powerful tools from becoming that Pandora's box we worried about?
This is a cornerstone of the whole GAN alchemist principle. It has to be proactively addressed. Let's break down the key areas. First, biosafety and biosecurity. This is critical for any prototype involving engineered microbes or CRISPR-edited crops released into the environment like the symbiotic farm, or even contain systems like the bio-AI cloud if there's a breach.
What does that involve?
It requires rigorous, mandatory, independent risk assessments before any release, robust physical and genetic containment measures in labs and early trials, and continuous long-term post-deployment environmental monitoring to detect any unintended spread or ecological effects. We can also design biological safeguards, like fail-safe genetic circuits.
Fail-safes, like what?
Things like engineered kill switches that activate if the organism escapes its target environment, or making the organism dependent on specific synthetic nutrients that aren't found naturally, so it can't survive long outside its intended niche. International treaties like the Convention on Biological Diversity and existing protocols like the London Protocol provide invaluable frameworks and principles for this kind of oversight.
Okay, containment and safety first. What's next?
Next is data privacy and equity. This is huge for the AI-driven prototypes. AI systems managing farms, like the symbiotic farm, or entire ecosystems, like the Planetary Symphony, will inevitably collect vast amounts of potentially sensitive data on land use, farming practices, local climate patterns, biodiversity, maybe even community activities.
That data is valuable and potentially sensitive.
Highly valuable. To avoid replicating historical patterns of, say, colonial extraction, where resources or knowledge were taken without fair benefit, data governance frameworks must be established from the outset. These must respect local control over data, ensure transparency in how data is used, and guarantee fair benefit sharing with the communities providing the data or stewarding the land. While open data practices are often beneficial for science, they must be carefully balanced with robust privacy protections for individuals and communities.
And the equity piece.
Critically, we need significant investment in capacity building, particularly in the Global South. This is necessary to prevent new forms of technological dependence, where only wealthy nations or corporations control these systems, and to ensure genuine, equitable participation in the development, governance, and benefits of these technologies.
So we're building the tech, but also ensuring who owns the data, who controls it, and that it doesn't just benefit the already powerful. What about fairness inside the algorithms themselves?
Exactly. That leads to algorithmic fairness. This is non-negotiable. The AI models themselves must be routinely audited for biases. Could the AI, for example, allocate resources like water or optimize seeds preferentially to wealthier regions or larger farms? Could it inadvertently ignore or devalue traditional or indigenous knowledge systems about land management, which often hold profound, locally adapted insights?
How do we prevent that?
We could establish community oversight boards involving diverse local stakeholders to provide review and input on AI decisions, particularly those affecting resource allocation or land use. Ethical guidelines must be embedded into the very design and training process of these AI systems from inception. And especially for something as ambitious as the Planetary Symphony, the principles of transparency and democratic decision-making regarding the AI's goals and operations would be absolutely fundamental.
Okay, safety, data rights, algorithmic fairness. What else?
Then there's consent and public engagement. This is vital for societal acceptance. All these prototypes, particularly those involving genetic modification, large-scale AI deployment, or climate intervention, absolutely require public buy-in and social license to operate.
How do we get that?
It means early, genuine, proactive engagement with all stakeholders, farmers, local communities, indigenous groups, the general public. It means using participatory design methods where communities can actually help shape how the technology is developed and deployed in their context. Things like citizen assemblies, accessible educational materials explaining the tech honestly, risks and benefits, and transparent communication are key. This directly echoes the London Protocol's emphasis on societal legitimacy and informed consent before undertaking potentially impactful activities.
Building trust through participation.
Yes. And finally, we need to think about intellectual property and access. There's a real risk that patents on new CRISPR seeds, engineered microbes, or core AI algorithms could severely restrict access, especially for smaller farmers or developing countries, concentrating the benefits in the hands of a few large corporations.
The IP barrier.
Right. We need to actively advocate for and explore alternative models like open licensing, patent pools, or commons-based innovation approaches. This helps ensure that the benefits of these potentially world-changing technologies are widely shared. Funding agencies and governments have a vital role here by incentivizing or even mandating open science practices for publicly funded research in these areas. The goal is ensuring these powerful tools serve humanity as a whole, not just enrich a privileged few.
This is our collective responsibility then. Making sure the tools we build are used for everyone's benefit, used fairly, used safely, and don't just create new forms of inequality or environmental harm while trying to solve old ones.
It has to be. Otherwise, the alchemy fails its core purpose.
Okay, so we've got the vision, we've thought hard about the costs, the funding, and the absolutely critical ethics and governance. But the big question remains, can we actually do this? What's the real-world feasibility of moving these ideas from the lab, from the blueprint, out into the world?
Yeah, the feasibility question, it really varies quite a bit across our three prototypes, reflecting their different levels of ambition and technological maturity. Let's break it down again.
Okay, let's start with technical feasibility. How realistic are these technically?
For the symbiotic carbon farm, technically it's looking quite feasible in the near term. It largely builds on existing, rapidly progressing technologies. CRISPR-edited crops with enhanced traits are already in field trials or nearing commercialization for some characteristics. Soil microbiome engineering is an active and advancing field, and sensor networks and AI for precision agriculture are already established commercial products. So the core components exist. The main technical challenge is integrating them effectively into a single optimized system.
Okay, so technically plausible soon. What about the bio-AI carbon cloud?
That one is definitely more speculative technically. However, it also primarily uses components that are individually established technologies. Biogas reactors are common, hydrogen electrolyzers exist, microturbines and fuel cells are commercially available, and cloud computing is obviously mature. The primary technical challenge here is the complex integration of these diverse biological, chemical, and digital systems, and then scaling them up reliably and efficiently. It requires significant systems engineering.
Integration is the hard part, and the planetary symphony.
Technically, that is truly visionary. Its feasibility hinges on major breakthroughs across multiple fields simultaneously. We need huge advances in the scale and precision of synthetic biology for ecosystem engineering, dramatic improvements in the power and efficiency of global-scale AI modeling and control, significant progress in remote sensing technologies, and, not least, unprecedented levels of sustained international scientific and political cooperation. It's currently beyond our technical grasp, but it sets a direction.
Okay, so a spectrum of technical feasibility. What about economic viability? Can these pay for themselves, or will they always need subsidies?
In the near term, economic viability looks potentially promising for the first two prototypes, largely thanks to climate policy. Carbon credits, carbon taxes, and climate-smart agriculture subsidies could make both the symbiotic carbon farm and potentially pilot versions of the bio-AI carbon cloud financially attractive investments, especially for early adopters.
How much do carbon prices matter?
A lot. We're already seeing carbon prices rising significantly in some markets, like the EU emissions trading scheme hitting 50, maybe even €100 per ton of CO2 equivalent. At those prices, technologies that offer verifiable negative emissions or significant emissions reductions start to look much more economically viable. The value proposition increases.
So policy is key to making the economics work initially.
Initially, yes. Long-term economic viability, however, will depend on continued supportive public policy, but also on consumer acceptance, driving market demand for food grown on carbon farms or services run on carbon-eating data centers, and continued technological learning reducing costs. For the Planetary Symphony, the economics are less about market viability and more about massive long-term public investment justified by avoiding catastrophic climate damages, a cost-benefit analysis on a planetary scale.
Okay, so the economics depend heavily on policy and markets, but what about the people? Societal acceptance, that feels like a huge factor, especially for GMOs and pervasive AI.
Absolutely. Societal acceptance is arguably one of the biggest hurdles, and it's crucial. Public perception of genetically modified organisms, GMOs, synthetic biology, and artificial intelligence varies widely across different cultures, regions, and even demographics within regions. There's no single global view.
So what influences acceptance?
Key factors include transparent communication, honestly explaining the science, the goals, the potential risks, and the safeguards. Active community involvement in the design and deployment process, so people feel they have a voice and agency. Demonstrating tangible local benefits improves soil, cleaner air, new jobs, not just abstract global ones. Rigorously addressing misinformation and disinformation, which can spread rapidly. And critically, conducting rigorous independent safety trials to build trust and demonstrate reliability.
Building trust takes time and effort.
It does. For the Planetary Symphony, given its immense scale and potential global impact, achieving societal acceptance would require an unprecedented international dialogue, deep public deliberation processes across many cultures, and ultimately a broad-based global consensus to grant it legitimacy. That's a monumental social and political challenge, perhaps even greater than the technical ones.
So, looking at feasibility overall, these prototypes aren't just wild dreams. They seem grounded in current or emerging science. They have plausible, albeit challenging, pathways forward. But their success hinges not just on technical breakthroughs, but equally on economic incentives driven by policy, careful ethical navigation, and crucially, earning public trust and acceptance. Our collective choices in terms of investment regulation, public engagement, and international cooperation will ultimately determine how quickly, how safely, and how equitably we move forward with these incredibly powerful synthesized tools.
That sums it up perfectly. The path forward requires a truly integrated approach, considering all these dimensions together.
We've journeyed through the individual elements, symbio, AI, CRISPR, climate engineering, ethics. We watched them combine and interact in the synergy forge. We've imagined the incredible, sometimes daunting prototypes they could yield. And now we reach the culmination, the magnum opus, perhaps the overarching principle that tries to encapsulate this entire deep dive.
Right. This culmination isn't just a summary. It aims to give us a much-needed framework, maybe a guiding star, for how we might collectively navigate these profound scientific, ethical, and societal opportunities and challenges ahead.
So what is this overarching principle? What name have we given to this concept we've forged through this deep dive?
We're calling it the Gaian Alchemist Principle, GAP.
The Gaian alchemist principle. Okay, break that down for us. What does it mean?
Okay, the name itself tries to capture the essence. Gaian refers to Gaia, the ancient Greek concept of Earth, as a complex, living entity. It emphasizes respecting Earth's living fabric, its intricate systems. Alchemist evokes that ancient aspiration of transformation, not turning lead into gold, but transforming disparate elements, in this case, knowledge and technologies, into something greater, something harmonious and valuable for planetary health. Principle signifies it's a guiding concept, a way of thinking.
So respecting the Earth system while trying to transform our interaction with it using synthesized knowledge.
Exactly. The principle embodies the core idea that solving our interconnected planetary crises, climate, energy, food, biodiversity, requires the intentional, careful fusion of biological systems, like engineered microbes or crops, digital systems like AI and sensors, robust ethical frameworks, and adaptive regulatory systems. The goal is to create a self-optimizing, resilient network that works with the planet's natural processes.
It sounds like treating Earth as a living, interconnected system and consciously using our most advanced tools to work with it, maybe even help heal it, rather than just exploiting it or trying to impose simple fixes.
That's precisely the shift in perspective GAP encourages. Its core tenet is that things like carbon management, renewable energy production, sustainable food security, biodiversity protection, and even potential climate interventions are not isolated problems to be solved one by one. They are deeply inseparable and must be understood, designed for, and governed as a single, holistic, integrated system.
Holism is key.
Yes. And GAP advocates for the purposeful coevolution of our technologies and our institutions. We need synthetic organisms co-evolving with AI infrastructures, which co-evolve with adaptive ethical guidelines, which co-evolve with responsive public institutions and governance structures. The ultimate aim is to achieve ambitious goals like stable net negative emissions, build truly resilient and equitable agricultural systems, ensure fair distribution of technology's benefits, and maintain ecological integrity.
That's a really ambitious and integrated vision. It's a lot to take in. Can you give us the elevator pitch for this Gay and Alchemist principle? Something concise that captures the essence quickly.
Let me try. Okay. The Gay alchemist principle proposes creating a symbiotic network where genetically engineered organisms help sequester carbon and enhance sustainable food production. Artificial intelligence optimizes renewable energy grids and monitors ecosystem health. Robust ethical governance ensures transparency, equity, and inclusivity. And any climate engineering is strictly limited and carefully regulated, all working together synergistically like a planetary symphony to harmonize technology with nature, aiming for net negative emissions and resilient, just societies.
Okay, that captures it. A symbiotic network, harmonizing technology and nature through integrated systems and strong ethics. If realized, even partially, the Gay and Alchemist principle could truly usher in a new era of climate stewardship, maybe even planetary stewardship. Instead of viewing technology primarily as an extractive force or even just a tool for efficiency, we would start to conceive of it as a potential extension of Earth's own metabolism, potentially capable of healing and regeneration, rather than just harm reduction. It's a profound shift in perspective.
It is. And just as the ancient alchemists believed that true transmutation required not only purification of the materials, but also purification of the alchemist's own soul and intentions.
Right, it was a spiritual or ethical quest, too.
Exactly. Our modern invention alchemy, guided by the Gay alchemist principle, would similarly require ethical purification. It demands embedding strong ethical considerations, ensuring broad social consensus and legitimacy for the powerful tools we create. The synergistic integration we've discussed, CRISPR crops, engineered microbes, AI-controlled renewables, prudent climate interventions could potentially create self-regulating ecological infrastructure.
Infrastructures that heal.
Infrastructures that actively draw down carbon, sustainably feed humanity, and power civilization, all while operating within and respecting planetary boundaries. But achieving this visionary future demands immense humility in the face of complexity, boundless creativity, and unprecedented levels of cooperation across disciplines, across cultures, across nations. It fundamentally invites all of us, scientists, engineers, policymakers, citizens, to become invention alchemists in our own way, to consciously participate in transmuting our knowledge, our technology, and our values into truly sustainable futures. So the question I'd leave for you, our listener, is what stands out to you most about this vision? And if you were to take just one small step towards becoming an invention alchemist in your own sphere, what might that first step be?
That's a powerful thought and a great question to leave everyone with the idea that we can all play a role, that we can be invention alchemists, actively shaping a better, more sustainable future for our planet. Thank you for joining us on this deep dive into the Gay and Alchemist principle.